Hi, welcome back. Today we're going to talk about some additional things related to derivatives of vector functions. First, let's talk about uh, nice functions. When we're talking in single variable calculus about a nice function, we'd often talk about continuous functions, right? That as long as you could draw them without picking up your pencil, you were kind of happy. Um, we're going to kick that up a notch. We talked about continuous functions, but let's also talk about a function being smooth. So when we're talking about a function being smooth, now it's not just that it is able to be drawn without picking up your pencil. We also kind of want this function to keep turning, but turning in a nice way. So we want it so that the derivative of the function, this tangent vector, is not equal to 0, except maybe at the endpoints. But what would it mean for this vector to be 0? It would mean that you came to a full stop at this point, and if you come to a full stop, then you can really turn in any direction from there. You can have a tangent in one way there and a tangent another way. It could occur that you have a cusp there. And so when we're talking about smooth functions, we want these functions to be those where we have no points where the function stops there. All right. So another thing that we might care about is you can take a derivative of a derivative, right? So the second derivative means take the derivative with respect to t once, take the derivative with respect to t another time. Great. Um, we can talk about the unit tangent vector. So we've been talking about a function, and if it's speeding along and slowing down at different places, it's a really useful concept to be talking about a vector that's tangent to the curve, but is always of length 1. So if you're going really, really fast in some places and really, really slow in other places, it's useful to just normalize the tangent vector and get the unit tangent vector. And so to do that right, how do you get a normal vector, a vector that's a unit vector? You take your vector and you divide by its length. All right. Here are some rules about derivatives. Derivatives and vector functions play rather nicely. Uh, if you take the derivative of the sum, you get the sum of the derivatives. Same thing with the difference. If we have the derivative of a difference, you get the derivative of the difference of the derivatives. You can factor out constants of your function. You can also so then there's also a product rule. So let's say you have a function that's not a vector function. So like t squared cosine of t, t squared sine of t. All right, this t squared, we can think of that as being t squared times cosine of t comma sine of t. We really have a vector function here, and we have a function, a single variable function of t here. And in that case, we can use a product rule. There's 3 of these here. We can do derivative of this single variable function times the vector function plus that single variable function times the derivative of the vector function. Similarly, if you have a dot product between R and S, you have a similar product rule that we're used to. R primed dot S plus R dot S primed. And the cross product too. R cross S, the derivative of that is r primed cross s plus r cross s primed. Right, so these are three variants of the product rule. And so you should just keep in mind that when you have a product and you're taking the derivative of a product, whether it's the cross product, the dot product, or a product with a single variable function of t, then you have to apply the product rule. And just like all the other ones, you can prove that this works by writing out all the special components and just checking to make sure, and then recombining the terms, it works out. And the last thing here, here's a chain rule, which says if you're taking a vector function of a single variable function, then you have to use the chain rule. So for example, if we had cosine of t squared comma sine of t squared, this is a cosine of t squared, sine of t squared. So this is r of t squared for r is equal to cosine of t sine of t. Right, you plug in the t squared here. If you have that, you can apply the chain rule. These, if you're comfortable with them in single variable, these should not feel so complicated. But let's talk about the simplest application of this principle and the calculus, these derivatives, and that's to the idea of motion in space. So as we've been talking about here, this the derivative of your function, of your vector function, is basically telling you the direction in which you're going at that point. Right? It's if no more forces were acting on you and you're in space, which direction would you go after there? You would kind of like leave the track and just keep moving in that direction. That would be your vector velocity. So the derivative of r is the vector velocity, so the direction in which you're going and then the speed at which you're going. And indeed, the magnitude of that vector is the speed of your particle. And if we take the second derivative of r, we get the vector acceleration, right? So the acceleration is in what way is the velocity changing, right? So the velocity was in this first direction, in the red direction, and then the velocity becomes in the green direction. There's some force, there's some acceleration happening that's turning the red vector into the green vector. And that's the change from red to green is the derivative. The derivative of the red vector gives us the green vector. I mean, this is, remember, the derivative is instantaneous. But so as the red vector changes, there's a force acting on it that's accelerating, changing the velocity. And indeed, right, so one of these ideas about from physics is that force equals mass times acceleration, and that equation, the idea of force equals mass times acceleration, is actually a vector idea. That is, if there's a force acting on some mass, then you're accelerating the mass. And by accelerate, we could be decelerating. We could, if you've got a bullet and your force is acting to slow it down, then you're decelerating it. But that's still a vector acceleration opposite the velocity of the particle. So this acceleration gives us a force, or the force would give us an acceleration. So this equation, which you normally have seen as force equals mass times acceleration, is actually a vector equation that relates the force of an object with the acceleration that is imparted on the object. So let's do some examples using this. So let's say we have a mass of 40 kilograms. All right, so that starts with an initial position of 1, 0, 0, and initial velocity. So we're at 1, 0, 0. We are moving at a velocity of, so that's 1 in the x direction, -1 in the y direction, and 1 in the z direction. So we're moving in this direction, and has an acceleration, so it's being accelerated in a certain way, related as a function of t. So find the position and the velocity of the particle as a function of t. So position and velocity, we have to start with acceleration and integrate. So if we have a of t is equal to 4t, 6t, 1, then the velocity of t is equal to 2t squared, comma, 3t squared, comma, t, plus our constant, plus some value v naught, let's say. Right, when you integrate, you have to get a constant of integration. So we can figure out what the constant of integration is by looking at the initial velocity. V of 0 is equal to, 0, 0, 0, plus 1, -1, 1. So that's telling us that this V0 is 1, -1, 1. So that tells us that V of t is equal to 2t squared plus 1, 3t squared minus 1, comma, t plus 1. And now we can use this to then find the position. The position s of t is the integral of this. The integral of 2t squared is 2/3 t cubed. The integral of 1 is t. The integral of 3t squared is t cubed minus t. And then the integral of t plus 1 is t squared over 2 plus t. And this is the initial position. So if we plug in s of 0, we get, 0, 0, 0 plus 1, 0, 0. This is our c. All right, so that gives us our equation for the position of the particle and the velocity of the particle as a function of time. Last thing here, determine the force that the particle exerts at time t equals 2. Maybe it's the force exerted on the particle at time t equals 2. So it's being accelerated in a certain direction. What's the force there? And so here we use force equals mass times acceleration. The mass is 40 kilograms, and the acceleration is 4 times 2, 6 times 2, comma 1. So if we want to, so this is the force, this is a vector, and we could just write out, let's see, 40 times 8 is 320, 40 times 12 is 480, 40 times 1 is 40. And so if we wanted the magnitude of the force, then what we could do is we could do 40 times the magnitude of 8, 12, 1. 40 times the square root of 8 squared is 64, 12 squared is 144, 1 squared is 1, so 40 square root of 208, 209. So, about 14 times 40, about, that would be the final magnitude. All right. Let's end today with a really cool example that I think is a surprise. So this is saying, show that if a particle moves with constant speed, the velocity and acceleration vectors are orthogonal. So what we have to do is we have to start out with this idea about what constant speed means, and then figure out what that means about velocity and acceleration vectors. All right, so constant speed. Constant speed is saying the magnitude of the speed is constant. All right, so what's the magnitude of the speed? We can write down an equation for magnitude of speed. Right, magnitude of speed is v dot v is the square root of this dot product is equal to c. And if the square root of the dot product is equal to c, then v dot v is equal to c squared, some other constant. All right, so this is a mathematical way to say a particle is moving with constant speed. All right, and so now we need to figure out something about the velocity and acceleration vectors. So let's use the derivative, since that's what we're thinking about these days. So let's take the derivative with respect to t of both sides of this equation. So the derivative of v dot v is equal to the derivative of c squared. Now c squared, c was a constant, c squared is a constant, so the derivative is equal to 0. And now we have a derivative of a dot product. So we have to apply that theorem that we had before, the product rule, and we get that v dot v primed plus v primed dot v is equal to 0. Oh wait, the derivative of the velocity is the acceleration. So we get v dot a plus a dot v is equal to 0. And so, and a dot v is equal to the same as v dot a. And so that's 2 times v dot a is equal to 0. So v dot a is equal to 0. And what does that mean? That means that the velocity and acceleration vectors are orthogonal. So this is a really cool example because it starts off with an idea involving the constant speed, and then we have to apply the derivative, we have to apply the product rule, and when we go through all those things, we get that the velocity and acceleration vectors are orthogonal. All right, thanks for your attention. See you next time.